All right. Hey, everybody. Welcome back. It's been a minute. We've been at school, so life has kind of been hectic. Yeah, I've been meaning to post more in terms of algebraic geometry content, and then also to refine some algebraic topology content. Honestly, I'm not super happy with what I have up at the moment. I feel like it's very kind of unstructured and confused. And I get it, like it's me learning it, but in as much as it's public. I've been planning to go and revisit some of that stuff. So expect that soonish. Yeah, so we've done some off-camera work because we just weren't able to record the last lecture that we did. But it was on I think the beginning of chapter 6 or either maybe 7. It's quasi-coherent sheaves 6. Yeah, beginning of chapter 6. So basically, it's just intro to quasi-coherent sheaves, and then today we're gonna finish that up and get into. We're gonna skip over some of the Jordan-Holder theorem because it's just not really one of those topics that's entirely pertinent to what we're doing. It's like it's a cool thing, but it's something you might have seen, or I know I saw in my abstract algebra class. Obviously, with a little bit less technology, but. Anyway, yeah, so I went ahead and wrote out all of the things going on from last lecture, and then we can go ahead and get into the new lecture. So first we have that the quasi-coherent sheaves are OX modules that glue on affine opens. Really, when we say affine opens, we mean things isomorphic to spec A for some A. And then the category of quasi-coherent sheaves, QCO, satisfies the affine communication lemma. I think we uploaded that. That was one of the last things we did when I was in Florida. So hopefully that's memorable for you all. But it basically has to do with shared properties of open covers or open affine covers of affine schemes, and kind of the relationship there. So we also said we defined a quasi-coherent sheaf on a reduced scheme to be torsion if its stalk at the generic point of every irreducible component is 0. That doesn't sound right. That sounds like that should be non-zero. No, it's 0. Okay. That doesn't really come up again, so I'm just going to skip over that. If I'm wrong, I'm sure someone will correct me in the comments. We talked about localization of quasi-coherent sheaves. So if F is a quasi-coherent sheaf, then basically localization commutes with the global sections functor, right? And namely, F is quasi-coherent in the case that alpha is an isomorphism. And so we can have something that's just an OX module, but alpha needs to be an isomorphism. We also established the sheaf of nilpotents, so it just follows this diagram. That's how you construct it, but it results in this property of the sheaf of nilpotents looks like this. Yeah, quasi-coherent sheaves obey standard tensor properties with a global sections functor. So basically, if you have your global sections functor giving you a section M and a section N, then, and respectively, if you have two quasi-coherent sheaves, F and G, I guess I didn't write that down. I probably should have. But yeah, if F and G are quasi-coherent sheaves, and you tensor them, and you take the global sections functor, then it pops out to be a tensor product of A modules of the sections. Similarly, restriction maps are localization. And so this is kind of an important thing that we get some mileage out of. And the real fundamental idea here is that things are nicer to compute on affine opens. Okay, so then we have that if X is a scheme and we have a function in the global section, then basically we can define the not vanishing set. And the reason why we use this notation instead of df is that df is reserved for the affine case, right? So if X is an affine scheme, then we'll say df. If X is any scheme, then we'll say xf. And having started Eisenbud and Harris's book on my own time for some research reasons, I can say that this is the more standard notation because it applies in generality. Yeah. So earlier I said that restriction looks like localization. That's the QCQS lemma. The way this is a very important proof. So if you're watching this and you're working along with us, so it has to do, there's an exact sequence that's given. I don't know the name of the exact sequence, but it's given in the problem for Vakil as a hint. What you do is you tensor on the right with the global sections functor localized at F, and then you show that that's an exact sequence. It's not too hard. You just kind of churn through the homological algebra. You know, drop something in the kernel, show that that's in the image, do back and forth for both, or show that it's an injective map and you have trivial kernel for some of them. Anyway, standard type thing. And then kind of as we're getting into the stuff with Jordan Holder, and then this next section 6.6, visualizing schemes, associated points, and zero divisors. We say that a module is finitely generated if this map here is a surjection. And of course, if it's full, then its image is the kernel, and so really we're saying that it's exact at M, right? Similarly, it's finitely presented if it has finite generators and relations, and then it's coherent if it's finitely generated, and then this map, the kernel of this map is finitely generated. Right? And you might be thinking, like, for a lot of our use cases, these are all the same thing. And really, the truth is that it relies on a Noetherian hypothesis. So if you can establish Noetherianness, none of this matters. But otherwise, for non-Noetherian rings or non-Noetherian schemes, it's very important to distinguish coherence from finite generation because they're not just the same thing. Finally, we say that a quasi-coherent sheaf is of finite type if the global section attributed to it from every affine spec A has a finitely generated A module. And so all of this is just kind of throwing down definitions that we can use later. And I imagine we'll use in the next few minutes. So Garrett, any questions or things that I didn't say or you want me to make clear before we continue?
Not that I can think of.
Okay. So there's a few definitions that end up being important from Jordan Holder. And just briefly explaining what Jordan Holder is. When we think about like factorizing a polynomial, right? Or factorizing a scheme into its irreducible components. Maybe I think at best we've said, well, it's because, Noetherian something or other, right? Like a good example is, why does the Grosvenor basis algorithm terminate? Well, it's Noetherian and it's an integral domain. Okay, well, but really the more fundamental thing going on is the Jordan Holder package. And so, yeah, basically all of section 6.5 is proving it. And so I'll go ahead and state it. So let me call this new stuff. New stuff. Okay, so consider a general abelian category C with an object M. Well, then we say that M is simple or irreducible if its only sub-objects are 0 and itself. And then we define a composition series. For M is a finite filtration or chain of inclusions. 0, x naught, x1, and it's finite because we're saying proper here. Otherwise, it could be a non-finite filtration. And then such that the quotients xi plus 1 mod xi are simple. Now, we've seen this before, right? Where have we seen this before, Garrett? I don't know if you'll remember this, but
Is
do you,
this
do you
finite abelian groups?
Close, yeah. It was when we did Galois theory last summer, and we were talking about the
Yeah.
solvability of the quintic, right? We said that a
Right.
group was solvable if basically there existed a composition series for it. And so we've seen this before, but now we're talking about in a general abelian category. So this is kind of the getting to the algebraic geometry of why solvable groups relate even vaguely to polynomials, right?
Right.
Like when we covered it last summer, we talked about it in terms of Galois groups, but that's not the only way to do it, and this is kind of the other way to do it, which makes for a very like interesting thing.
Cool.
Anyway, but yeah, so then definition, if has a composition series, has finite length. Okay, and so then the Jordan-Holder theorem, and I'm assuming I'm pronouncing the O correctly there, but I might not be, is that if has a finite composition series, then all composition series have the same length. And all quotients are the same, possibly rearranged. And so then, yeah, we call this length, the length of M, but L of M is the length of the composition series, if it exists. Otherwise it's infinity. Okay, so this is just kind of something small. I don't want to spend a ton of time on this, but it's interesting. There's definitely some stuff, to play around with. But yeah, it's just not something that I care about too much. But there are some definitions at the end of this section that we want. And so I figured, hey, while we're here, let's go ahead and tie that in. Okay. So, yeah. As a definition, we say that if a ring A has finite length as a module over itself, meaning that it's a module of one dimension, right? So it's really just treating it like A, but you're looking more at the scalar multiplication and abelian addition property. Then A is an Artinian ring. And if A is a local ring, we say that A is an Artinian local ring. You know. And so kind of an example of applying this idea to schemes is that the simple quasi-coherent sheaves are isomorphic to sheaves of closed points. Right. And I think that this just makes a lot of sense, right? Like this is saying, if you are relying on the idea that quasi-coherent sheaves are glued together by generic points, you're saying that the generic points are the entire set. And so
Yeah, that
simple
makes
quasi,
sense.
yeah, so simple quasi-coherent sheaves are like kind of these easy to study ones because the whole like thing on the open is determined by the generic point, and that is the whole thing. Um, yeah. Okay, and then definition is that the length of a scheme X is the length of Ox in the category of quasi-coherent sheaves. And then, of course, this extends our idea of an Artinian ring, but a scheme is Artinian if its structure sheaf is Artinian ring in quasi-coherent category. Right. And so all of this is chapter 6.5. So I think that this wraps up pretty nicely. I don't have anything left here that I'm like itching to uncover. Do you have any questions?
No, I do not.
Okay. So now what we're going to talk about is once again visualizing schemes by associated points and zero divisors. So the theory of associated points of a module refines the notion of support, and associated points will help us understand and visualize nilpotence and generalize the notion of rational functions to non-integral schemes. So they are useful in ways that we won't use, for example, through their connection to primary decomposition. I don't really know what that is, so I'm not going to talk about that. They might be most useful for us in helping us understand and visualize non-zero divisors, which will come up repeatedly through effective Cartier divisors and line bundles, regular sequences, depth, and Cohen-Macauliness, and more. This section can be read basically independently, but with where I kind of want to take us, it's pretty important. So, because it sets up the idea of line bundles. So this is kind of an aside. Feel free to skip this if you're watching this and you're not like friends with me or trying to do research with me. But the research that I'm working on right now is in Schubert calculus. And, kind of as I've learned algebraic geometry and really kind of tried to like get a grip on it that's strong enough to like do research. At first it was kind of like, okay, well, algebraic geometry is about varieties. I was like, okay, well, algebraic geometry is about sheaves. Okay, well, algebraic geometry is about schemes, but schemes are varieties. Okay, that's weird. Okay, well, then maybe algebraic geometry is about like cohomology is like a tool for understanding like the bookkeeping of geometric properties. Okay, well, cohomology is really about line bundles. Line bundles are really just invertible sheaves. And so algebraic geometry is really about line bundles. And that's kind of where I'm at now. And I'm sure that will change. But yeah, the work I'm doing in Schubert calculus has to do pretty heavily with line bundles. So kind of my plan is to get us through chapter 6, chapter 7, chapter 8. But then really I want us to focus on chapters 9 and later, really 9 through I think about 18. And then once we get up to 18, we can kind of start, maybe even up to 16, we can start switching between Eisenbud and Harris and Vakil, just kind of as we're doing it. So the difference is, so Vakil, kind of the first, I think, 12 chapters are like, here are all of the definitions you need kind of to have the building blocks of algebraic geometry. And then the later stuff is a lot of advanced stuff kind of written the way that Vakil likes to think about geometry. Eisenbud and Harris kind of picks up with the goal of tackling intersection theory. So it's a second course in algebraic geometry. Intersection theory is the theory of intersections of curves or surfaces, right? So intersections of varieties, of course, form varieties, and so we want to be able to think about and characterize those in interesting ways. Intersection theory is inherently combinatorial, and so right now my work is in combinatorial geometry, and specifically in Schubert calculus. And so I'm very interested in going through 3624 and all that for a few reasons, but really largely because it's very relevant to kind of what I'm trying to work on. And so really I'm trying to compute right now the cohomology ring of this really weird set that's a subset, definitely not a subgroup or subring of the symmetric group of 2n letters. And it has some really weird properties geometrically, and nobody's really cared enough to do it before, and that's where I come in. And yeah, there's just a ton of stuff, and every single time I think I'm like getting a handle on this, there's always like one more book I need to read because of like 3 papers that end up being super important. And at this point, it's just like, oh my God, can I please, like, this is not a Noetherian scheme. This algorithm is not terminating, you know? So anyway, rant aside, the stuff that we're doing is going to be kind of just pertinent to that. I think, Garrett, for your and my project, we've kind of passed the point of like what you need to work on Dr. Scott's stuff. So we're doing this really more because it helps me a lot to work on this stuff.
Awesome. Doing it for the love of the game.
Exactly. And also, like, even without the research project, it's very interesting. But I have the external motivation of an advisor who believes in me, and I'm very grateful for that. So I like to kind of push in that direction. Okay. So motivation. So if we have so 6.6. So if we have like a line, and maybe I'll highlight this line. It's highlighted in the book. And maybe on this line, we have a point. And then maybe we have another line that's kind of up some. And then maybe we have a curve that intersects this line somewhere. But really, we're thinking of another specific point here. So in this figure, we have the sketch of a scheme. We see we have 2 connected components and 3 irreducible components. So the irreducible components of X have dimensions 2, 1, and 1, although, I mean, no, we can make sense of the idea of dimension, like we talked about Kroll dimension in Hartshorne. And then both connected components are non-reduced. So we see a little more in this picture, which we will make precise in this section in terms of associated points. The reducible connected component seems to have different amounts of non-reduced behavior on different loci. So the scheme X has 6 associated points, which are the generic points of the irreducible subsets visible in the picture. And then a function on X is a zero divisor if its zero locus contains any of these 6 irreducible subvarieties. So I'm a little confused at how the word zero divisor is being used. I don't think it's in the sense of integral domain. I think it's in the sense of a vial divisor, uh, which we have not been. I have been working with, but we haven't talked about on this channel. So I'm assuming that this will be well defined soon. So, okay, suppose that M is a finitely generated module over an Noetherian ring A. For example, M could be A itself. Then there are some special points of spec A that are particularly crucial to understanding the module. These are the associated points of M, or equivalently, the associated prime ideals of M. These are kind of interchangeable terms because of the bijective correspondence that we've spent months building up. So as a motivation, we give a zillion properties of associated points and leave it to you to verify them from the theory developed in the rest of the section. So just keep in mind convention/example. Let M be A, be K of X over Y, where K is a field, mod Y squared and XY. So what does this look like? Well, we are gluing the axes and we are gluing the parabola. And all of these are identified with 0. And I need to plug in my laptop really fast. Okay. Right, I forgot that this room doesn't have. 1 second. Okay, so why is this a good or an interesting example? Well, we have like a really singular point, right, at 0. And so this is one that I'm assuming the idea is we're going to be thinking, all right, let's pick an open subset here, and then any divisor we construct in that open section is going to be a 0 divisor. But I don't know. That's my guess going into this. It's a hypothesis. So let me find the definition of a freaking associated point. Because there we go. Okay, the associated prime ideals of an A module M are the prime ideals of A of the, oh, okay. Okay. All right. I'm gonna do this in the order that he does it because I read through this section. And then if it doesn't make sense, it doesn't make sense. Okay, so facts. So there are finitely many associated points. And yes, that really is the abbreviation for it. I don't know what to tell you. I hope YouTube doesn't like take down this video over that. That would kind of suck. This is the notation for it, like canonically. So
That's amazing.
yeah.
This made my night, Tim.
Well, I'm glad. So the support of M is the closure of the associated points of M. So the support of M is that the support of any submodule of M is the closure of some subset of the associated points of M. The support of any element of M is the closure of some subset of the associated points. The associated points of M, are the generic points of irreducible components of sub M for all little m in M. So again, generic points are points whose closure is the entire set that they're in. And really, they're the points that we think of as carrying the global data in a sheaf. The associated points of M are precisely the generic points of those sub M that are irreducible. The associated primes of M are precisely those prime ideals that annihilate some element of M. So the SAM are ideals which annihilate M and M. So localization commutes with taking associated points. Hence, this notion is geometric in nature, which will allow us to extend the notion to coherent sheaves on locally Noetherian schemes. All right, associated points behave fairly well in exact sequences. For example, the associated points of a submodule are a subset of the associated primes or associated points of the module. If I contained in A is an ideal, the associated primes of A mod I as its own module, and primes P in the associated primes are precisely those that have a P primary module appearing in the decomposition of I. So an element M in A is a zero divisor if and only if it vanishes on an associated point. And then M in A is nilpotent if and only if it vanishes at every associated point. Okay, and then the locus of points P in spec A, where AP is non-reduced, is the closure of some subset of the associated points. An associated point that is in the closure of another associated point is called embedded. If A is reduced, then spec A has no embedded points. Hypersurfaces in AN and intersections have no embedded points. Okay, elements of M are determined by their localization at associated points. Oh my God, there's so many sections of the sheaf are determined by germs at associated points. My hand is getting tired. Okay, so the discussion immediately implies the notion of an associated point for a coherent sheaf on a locally Noetherian scheme with all the good properties described here. The phrase associated point of OX, the phrase associated point of a locally Noetherian scheme X without explicit mention of a coherent sheaf means associated point of the structure sheaf. And similarly for embedded points. Okay. Now we're going to establish all of these facts. Maybe not in the next 20 minutes, actually. But we're going to do some of it, and that's what matters. All right, so recall some definitions. If M is in M, then sup little m is the set of P in spec A such that M localized to P is not zero. And this is really some VI for some I. And then we're going to define the annihilator ideal. And A of M contained in A of M in M in mod A is given by the set of A and A such that AM is 0, which is the kernel of the map going here. And that's the same thing. We'll usually omit this subscript A as long as the context is clear. And so theorem is that the support of M is actually the vanishing of the annihilation of M. Let's see. Give me 1 second. I want to just take a look on where I want to get to by the end of tonight. Okay. Yeah, so really what we want to do is we know this, right? Like we know that sup M is the vanishing of some ideal, and we just want to show that, if you have P in um, um, sorry, 1 second. So P in sup M has that MP is not 0. But then the annihilator of M has that it's the set of all of the things which vanish on M, right? So it's the A and A such that AM is 0. Well, the vanishing of this would be that this is all of the stuff. This is the set of all A over B such that B is not in P. And so meaning that MP corresponds to the vanishing on P for some schemax. But then the vanishing on P is really going to be in the annihilator. Right. So and so this is kind of how we get our first containment. And this is proof sketching. I'm gonna have to go in like a few minutes, but I want to finish with this exercise, I think.
Yeah, no problem.
So this is loose. I'm gonna work it all out a little bit more off camera because I have to go.
Yeah, no
But
problem. I
this
have
this
2 quizzes tomorrow, so.
oh yeah. Well, this gives basically sup M contained in the vanishing of the annihilator, right?
Yeah,
And
that
then
works out.
the other direction is if we let, alpha in the annihilator, well then alpha M is equal to 0. And so then the vanishing of alpha M is exactly all of the prime ideals which vanish on alpha, right? So it's all of the P in spec A such that P P contains the vanishing of alpha. Right? And so in this way, this is clearly the support of M, right? And then it's just
Yep.
kind of the bundling of all of those together. And so then this gives us that V is contained in sup. So I encourage, of course, working this out more thoroughly, but for now, not terrible. Any questions before I turn off the recording real fast?
Nope.
All right. Well, thank you all for tuning in.